welcome to another module in this massive open online course on estimation for wireless communication systems. Today we are going to look at channel estimation and specifically MIMO channel estimation, where MIMO stands for multiple input, multiple output. So we are going to look at channel estimation of a multiple input, multiple output or a MIMO wireless communication system, right. So today let us start looking at, today let us look at MIMO channel estimation, where MIMO, as we said, it stands for multiple input, multiple output, where as we said MIMO, this stands for multiple input, multiple output. So MIMO stands for multiple input, multiple output, and in particular the multiple inputs that we are referring to are the multiple transmit antennas. So through the multiple transmit antennas, the multiple input symbols are transmitted, and simultaneously the multiple outputs that we are referring to correspond to the multiple receive antennas. So the multiple output symbols are basically received through the multiple output antennas. So multiple input, multiple output communication system basically means a wireless communication systems which has multiple transmit antennas at the transmitter and multiple receive antennas at the receiver, alright. So this multiple input refers to the multiple, this refers to your multiple transmit or TX antennas, and the multiple output, this aspect refers to the multiple, when we say multiple we mean more than one, multiple receive, multiple transmit antennas and multiple receive antennas. That makes a MIMO wireless system. For instance, let us consider a simple MIMO system with 2 transmit antennas and 2 receive antennas. So I am drawing here a simple MIMO system, a schematic diagram of a simple MIMO system. This is my TX, that is transmitter, this is the RX, that is the receiver, and this basically has, let us say to consider a simple example, this basically has 2 transmit antennas and also 2 receive antennas. So we are considering a simple MIMO system which has 2 transmit antennas and 2 receive antennas. This is known as a 2 cross 2 MIMO system. If you have R transmit antennas and R receive antennas, it is known as an R cross T MIMO system in general, right. So this is a simple example. This is a simple example of a 2 cross 2 MIMO system. A simple example, also this is 2 transmit antennas and these are your 2 receive antennas, and this is termed as a 2 cross 2 MIMO system. In general, for R receive comma T transmit antennas, we have an R cross T we have an R cross T MIMO system. So, here we are considering a 2 cross 2 MIMO system, and now therefore, let us denote this transmit antennas by T1, transmit antenna 1, T2, transmit antenna 2, R1, receive antenna 1, R2, receive antenna 2. Alright. So, let us denote the channel coefficient between transmit antenna 1 and receive antenna 1 by H11, between transmit antenna 1 and receive antenna 2 by H21. Similarly, let us denote the coefficient fading channel coefficient between transmit antenna 2 and receive antenna 1 by H12, and let us denote the coefficient between transmit antenna 2 and receive antenna 2 by H22. So, naturally we have 2 transmit antennas and 2 receive antennas. So, basically we have 4 wireless links, right, because between each pair of transmit and receive, that is between each transmit and receive antenna pair we have a channel. So, naturally since we have 2 transmit and 2 receive antennas, we have 4 basically links or basically which are characterized by 4 channel coefficients, that is 2 times 2, that is 4 channel coefficients. In an R cross T system, of course, you have R times T, that is R into T channel coefficients. And notice that we are denoting this channel coefficient using the notation Hij, where Hij is basically the channel coefficient between the receive antenna I and transmit antenna J. So, this channel coefficient Hij, so Hij is the channel coefficient between the ith receive antenna. So, this is the channel coefficient or also the flat fading channel coefficient between your ith receive antenna and the jth transmit antenna. For example, if you take a look at the channel coefficient H21, H21 is the channel coefficient between the second receive antenna and the first transmit antenna, that is H21. Okay. So, if you take a simple example H21, this is the coefficient between TX antenna 1 and RX antenna 2. And further, now if we look at our MIMO system, let us consider the symbol X1 transmitted from transmit antenna 1, X2 transmitted from transmit antenna 2, Y1 received on receive antenna 1, Y2 received on receive antenna 2. So, generally speaking, Xj is basically the symbol, or Xj is the symbol that is transmitted on transmit antenna J, and Yi is the symbol that is received on receive antenna I. Okay. So, Xj is basically symbol transmitted on transmit antenna J, and Yi is the symbol received on receive antenna on the receive antenna I. So, Yi is given as, now let us write the equation for Yi equals Hi1 times x1, that is Yi at time instant k equals Hi1 times x1 k plus Hi2 times x2 k, that is symbol transmitted on transmit antenna 2 at time instant k, plus Hit, since there are T transmit antennas, Hit times x t k plus v I of k. So, this is the symbol received on receive antenna I, that is y I k is the symbol received on receive antenna I at time instant k, is basically, for instance, you can see this is h I 1 times x 1 k, that is the coefficient between receive antenna I and transmit antenna 1 times x 1 k, that is x 1 k is the symbol transmitted on transmit antenna 1, plus h I 2, that is coefficient between receive antenna I and transmit antenna 2 times x 2 k, the symbol transmitted on transmit antenna 2, so on and so forth till h I t times x t k, where x t k is the symbol transmitted on transmit antenna t at time k, plus v I of k, that is the noise sample at receive antenna I at time instant k. For instance, now let us look at this in the context of our 2 cross 2 system, specifically for our 2 cross 2 system. So, specifically we have y 1 of k on receive antenna 1 is h 1 1 times x 1 k plus h 1 2 times x 2 k plus v 1 k. Similarly, y 2 k equals h 2 1 x 1 k plus h 2 2 x 2 k plus v 2 of k. Now, what are these? Basically, your y 1 of k is symbol on receive antenna 1 at time k, and your y 2 k is basically symbol on receive antenna 2 at time k. Similarly, x 1 k, this x 1 k, again just to repeat it, x 1 k symbol transmitted on transmit antenna 1 at time k, and x 2 k is symbol, is basically your symbol transmitter on transmit antenna 2 on TX antenna 2 at time k, and similarly your V 1 k and V 2 k, basically if you look at V 1 k and V 2 k, they are the noise samples on receive antennas 1 and 2 at time instant k. Okay. So, V 1 k what are these? These are noise samples on receive antennas 1, 2 at time k. These are noise samples on receive antennas 1, 2 at time k, and therefore, now what I am going to do, I am going to write this 2 cross 2, that is this input output model for this 2 cross 2 MIMO system using vector notation, and I can write this as follows using vector notation. I can write this as basically your y 1 k equals H11, H12, H21, H22 times X1k, X2k plus the noise vector V1k, V2k, where Y1, Y2 this is the receive vector, which is R cross 1, or in this case since R equals 2, basically 2 cross 1. This is your channel matrix, which is R cross T, in this case 2 cross 2. This is your transmit vector, which is X bar, which is your transmit vector, which is your transmit vector, which is T cross 1, in this case 2 cross 1, and this is your noise vector V bar. This is the noise vector V bar, which is basically R cross 1. So, if I am just write it a little bit more clearly below. So, this is Y bar of k, which is your receive vector, equals H, the channel matrix, the MIMO channel matrix H times X bar k plus V bar k. So, Y bar k is, this is your receive vector, which is R cross 1. This is the MIMO channel matrix, which is R cross T. This is the transmit vector, which is T cross 1. And this is the noise vector, which is basically R cross V bar is the noise vector at time instant k, which is R cross 1. So, we have the MIMO system model, which is Y bar k, that is the received vector, received symbol vector at time instant k is equal to H, that is the R cross T MIMO channel matrix, times X bar k, where X bar k is the transmitted symbol vector at time instant k, plus V bar k, which is the noise vector at time instant k. Okay, this corresponds to a single time instant, that is the transmission of the symbol vector, or in our case of estimation, that is the pilot symbol vector X bar of k, and the reception of the corresponding received vector Y bar of k. Now, since we have T transmit antennas, we are transmitting T symbols, therefore, X bar of k has the T transmit symbols, therefore, it is a T cross 1 vector, or a T dimensional 1 vector, and since we have R receive antennas, basically we are receiving R output symbols, right. Therefore, the output vector Y bar of k is R dimensional, it has the R output symbols, alright, and this corresponds to the model of an R cross T MIMO system, that is multiple input, multiple output. Since we have multiple inputs from the T transmit antennas, multiple outputs from the R receive antennas, this is the model of the R cross T MIMO system, which is captured basically by this R cross T MIMO channel matrix, which consists of the channel coefficients between each pair of transmit and receive antennas, correct. And now what we want to do in MIMO channel estimation, we want to estimate this MIMO channel matrix. Therefore, the problem of MIMO channel estimation, now if I can motivate it better, is to estimate this channel matrix. Problem of MIMO channel estimation is to basically estimate the channel matrix H. Estimate the channel matrix H. And similar to channel estimation that we have seen earlier, we will consider transmission of pilot symbols. However, we are now considering a MIMO channel, therefore, we have to transmit pilot symbol vectors. right. At each instant we are transmitting a t dimensional vector, we are receiving an r dimensional vector. So, for MIMO channel estimation we will transmit t dimensional pilot vectors and we will receive corresponding r dimensional pilot output vectors, that is the y bars, correct. So, let x1 bar, so let us denote the pilot vectors. Let us consider the transmission of n pilot vectors. Consider transmission of n pilot vectors. These n pilot vectors, these are given as x bar of 1, x bar of 2, so on x bar of n. What are these? These are basically your n pilot vectors, and corresponding to these transmitted n pilot vectors we are going to have n output vectors. Each pilot vector results in an output vector, alright. So, corresponding to each of these pilot vectors we are going to have an observed vector y bar, alright. So, naturally let us now denote the system model by y bar of 1 equals h times x bar of 1 plus v bar of 1, y bar of 2 equals h times x bar of 2 plus v bar of 2, and so on so forth. We have y bar of n equals h times x bar of n plus v bar of n. Therefore, now if I look at the output vectors y bar 1, y bar 2, if I stack my output vectors, now I can stack these output vectors. What I am doing is basically I am stacking them basically row wise, right, y bar of 1, y bar of 2, so on y bar of n. So, basically now what you can see is basically you will get each vector is r dimensional and I have n such vectors. So, this is an r cross n matrix, correct, and this is basically equal to your h times correspondingly x bar of 1, x bar of 2, x bar of n, and naturally what is this matrix? This basically each vector is t dimensional, I have n such vectors. So, this is a t cross n matrix. Let us denote this by x, this is your pilot matrix. Let us denote this by y, this is the received vector matrix. Of course, your H is your channel matrix, which is still your R cross T matrix, plus of course, I have a noise matrix, which is V bar 1, V bar 2, V bar n. This consists of n vectors which are r dimensional. So, r dimensional vectors n of them. So, this is R cross n matrix again, and let us call this as V. And therefore, now after we concatenate this, that is we look at these n transmitted pilot vectors and we look at the corresponding n received output vectors y1 by y bar 1, y bar 2, y bar n corresponding to the transmitted pilot vectors x bar 1, x bar 2, x bar n, and now I can write the system model as y equals hx plus v, correct. And therefore, so now where y, as we have shown, this is r, just to repeat this is r cross n, is r cross t, this is a t cross n consisting of the n pilot vectors, and this is basically your r cross n matrix. Now, this is similar to your y equals remember the kind of system model that we had for multi antenna channel estimation, except there we had y equals xh. Now, here we are seeing we have y equals hx, this is more standard notation for MIMO. So, let us just recast it in a form that we are already familiar with. So, I am going to take the transpose of each quantity. So, I can write taking the transpose of the quantity, taking the transpose on left and right, taking the transpose on left and right, what do we have? We have y transpose equals x transpose h transpose plus v transpose, and therefore, now you can see this is of the form y equals xh, and now I can formulate my least squares problem for channel estimation similar to the multi antenna case. Least squares problem for channel estimation, that is given as y transpose minus x transpose h transpose whole square. This is my least squares problem for channel estimation, and except here there is a slight change. This is the matrix Frobenius norm of the matrix, because now we are dealing with matrices, we have to consider the Frobenius norm of the matrix, but do not worry too much about this. Basically, this can be formulated as a least squares problem, and the corresponding solution can now be given as the pseudo inverse of x transpose times y. So, the corresponding least squares estimate of h transpose, remember we have formulated the problem in terms of the transposes, that is the pseudo inverse of x transpose, which is basically x transpose times x transpose inverse x transpose times basically your y transpose, and that is equal to basically x transpose inverse x times y transpose, that is the estimate of your transpose of the MIMO channel matrix. Therefore, now taking the transpose of this, the estimate can be obtained as h hat equals the transpose of the estimate transpose, which is basically y x transpose into x transpose inverse, and that is basically your MIMO channel estimate. In fact, this is the least squares MIMO channel estimate. So, what we have shown is basically when you concatenate these corresponding received vectors, received pilot vectors y1 bar, y2, y bar 1, y bar 2, y bar n as the matrix y, as the r cross n matrix y, and the corresponding transmitted pilot vectors as the t cross n matrix x bar 1, x bar 2 up to x bar n, alright, and call it the matrix x, then the least squares estimate of the MIMO channel matrix based on minimizing the least squares norm of the least squares norm, or in this case the least squares Frobenius norm of the error, that is given as y times x transpose times x transpose inverse. Okay. So, that is the least squares estimate of the MIMO channel matrix. So, let me repeat that, just write it down again. H hat, to summarize, h hat equals least squares estimate of least squares estimate of the MIMO channel matrix. I have y, which is equal to y bar 1, y bar 2, so on up to y bar n, this is an R cross n matrix. I have x, which is basically the matrix of pilot vectors, that is x bar 1, x bar 2, so on up to x bar n, and h hat, the least squares estimate, or basically also the maximum likelihood estimate, is therefore equal to y x transpose times x x transpose inverse. This is the estimate of the MIMO channel matrix. And so, what we have done is we have achieved something significant in this module. What we have started with is we have now considered a very general scenario of a multiple input, multiple output wireless channel. Remember, we first started basically with a single input, single output wireless channel, the very first example where you had a single transmit antenna and a single receive antenna. Slowly we extended it to a multi antenna communication system, that is where we had multiple transmit antennas. Remember, we considered a downlink transmission scenario where the base station had multiple antennas and the mobile had a single receive antenna. We termed that as a multi antenna channel. Now we have extended it to a very general multiple input, multiple output scenario where there are multiple inputs or multiple transmit antennas at the transmitter as well as multiple outputs or multiple receive antennas at the receiver. We have formulated this system model for this MIMO wireless system in terms of the matrix channel, in terms of the channel matrix H. And now we have also given or derived the least squares or maximum likelihood estimate of this MIMO channel matrix H based on the transmission of n pilot vectors x bar 1, x bar 2 up to x bar n, and the corresponding received vectors y bar 1, y bar 2 up to y bar n. And if the received matrix is denoted by y, the transmitted pilot matrix is denoted by x. We have said that the MIMO, we have derived that the MIMO channel matrix estimate H hat is given as y x transpose times x x transpose inverse. And in the next module, we will look at a simple example to basically solidify this concept, sort of make this even more clear. Alright, so we will stop this module here, we will continue in the subsequent module. Thank you.